After having seen what is not a vector space, so in the previous video we have seen an example of something that is not a subvector space. Let's see now what is the prototype of all the subvector spaces. So notice first that we can sum up the two conditions for a subset of a vector space to be a subvector space in a unique one. So let V be a vector space and W inside V a subset. Then W is a sub-vector space of V if and only if alpha times W1 plus beta times W2 belongs to W for every alpha and beta scalars and W1, W2 elements in W. Okay. You see, this element contains both sums of V inside V and multiplication by scalars. So this element is obtained through both the algebraic structures of V. So this is a vector, of course, and it is a special case of particular vectors of this form. Definition: let S in V vector space be a subset a linear combination of vectors in S is a vector of the form V equals sum for I that goes from 1 to n of lambda I times Vi, where Vi's are all elements in S. So what is a linear combination? A linear combination is a sum of certain vectors. The summands of this sum are of the kind lambda I, where lambda I, they all belong to the field K. So lambda I times certain vectors Vi that have to stay in S. So it's extremely important that we are considering here finite sums. So S has no restrictions on it, can be finite or infinite, but the sum that we are taking here is certainly finite, and this number n is not relevant. It can be anything, but has to be finite. So each of these sums involves a finite number of summands, but they are not uniformly bounded or anything. They are just, each of them is finite. That's all. There is a very important concept, which will, well, object, let's say, that we will indicate with the particular notation. So let's say notation. We will denote by S with these two angular brackets the set of all the linear combinations of elements in S. Okay, so in other words, S is going to be, as a set, all the vectors of this form. I goes from 1 to n lambda I times vi, such that lambda I belongs, each lambda I belongs to k, vi belongs to S, and n is a positive integer. The fundamental fact regarding this set is the following proposition. The set S with this angular bracket is a sub-vector space of V. Okay? So how do we prove this? So we simply use the definition that involves the two conditions a set has to satisfy in order to be a subvector space. So you remember, it has to be closed under sum, the sum of V, and has to be closed under multiplication by scalars with the same multiplication as inside V. Okay. Okay, so let's check this out. So first we take two elements in this set, so two linear combinations, and we verify that the sum of them is again a linear combination of elements in S. So let's take one linear combination. We use the same notation as the one here. Let's say from I that goes to 1 to n lambda I times vi. And then we take another linear combination. Let's call it sum from j goes to 1 to m alpha j times wj. So to check, sum of these two elements, I goes from 1 to n lambda I times vi plus sum per j that goes from 1 to m of alpha j times wj still belongs to this set. But all these elements are linear combinations. Okay, linear combination of elements in S. Okay, so we replace this condition by is a linear combination of vectors in S. But this is obvious because if we just expand this sum, we will have a series of summands of this form where all the vi's belong to S, and then we just juxtapose on the right hand side a series of m summands. Each of them are a coefficient, like a scalar, times wj, where wj as well belong to S. Okay, so gathering all these summands together, we will be getting a unique big sum of vectors in S, multiplied each in front by scalars. Okay, so this is precisely one of the linear combinations inside S. So this is pretty clear. The same goes for the second property. So we consider again some linear combination, sum from I that goes to 1 to n, lambda I vi. We multiply this element by an element, a scalar, any scalar. Let's call this lambda. Okay, and we want to prove that this is a linear combination of elements in S, of vectors in S. Okay, in this case we just apply the distributive property of a multiplication of a scalar through the sum in V. This is one of the axioms that the multiplication with scalars has to satisfy, if you remember, if you go back to the definition of vector space. Therefore, this sum multiplied by lambda in front is precisely this vector sums for I that goes from 1 to n of lambda times lambda I times vi, where this multiplication is inside K, this multiplication is inside V. This element is an element in K for each I, because it's the product of two elements, two scalars. Therefore, this is a perfectly legitimate linear combination of vectors in S, which are the VIs. The scalars in front of the VIs have changed, but nonetheless they are elements in K. Therefore, this is a linear combination of elements in S.